Swayam Prabha. Digital India. Educated India.
Okay, so let's continue our discussions related to sinusoidal analysis of linear circuits. And today we'll look at a concept of frequency response. So the idea is that if we look at a signal, the signal could be audio, speech, or a video signal, or all kinds of signals from the, let's say, ECG signal. Any of those signals, if we examine, often when we look at the signal in the time domain meaning that we look at how the signal or the amplitude of the signal is varying as a function of time, like the signal over here, one can understand something about the signal, but often one is not able to get a lot of insight into the nature of the signal. For example, if we see the signal over here, we can see that there is a rapid variation in signal, and along with that there is perhaps this envelope that you see here. There is a slower variation also, but it's hard to see those things. Maybe there are even more variations embedded in it which we are not able to see. And so in that context, what we'll see today in this lecture is that instead of looking at signals in the time domain, not just looking at signals in the time domain, if we analyze the signal in the frequency domain, we may get additional insight, additional understanding of the circuit, which would help us in designing systems as well. All of us remember, the first time we saw a prism. And it's fascinating to see how a white light or a normal light, if you pass it through a prism, and it breaks up into these different colors, which of course are of different wavelengths, different frequencies that are there here. And so it allows us to see this prism is like a frequency analysis of let's say a white light here. So it does a frequency analysis of white light by breaking it up, by allowing us to see what are the different frequency components in that white light that is there here. And so this is not just helps us understand the composition of a white light, but when you see a screen like this on your mobile or in your laptop, and you see a white region that is there here, so the white region is being generated through a combination of some amount of red and some amount of green and some amount of blue. So the fact that the white light is made up of red, green, and blue in certain proportions allows us to create, for example, in the screen, we don't have normally we don't have a white LED, let's say. If it's an LED based display, we don't have, let's say, a pure white LED. Even when you see white LEDs in your homes, that white LED, the color white is obtained by combining let's say a blue with an orange or other colors, maybe a red, green, and blue in suitable proportion. So when we analyze, so this is an example of when we analyze something and break it up into its frequency components, it helps us gain insight into it. And of course, we use that insight to create new systems, create or modify new systems with that insight. So in laboratory, for example, we have an instrument called a spectrum analyzer. So whatever signal that you capture, let's say you capture a ECG signal, and you can feed it into your spectrum analyzer, and it will tell you the spectrum of it. Meaning, let's say if I take this particular signal that I just showed you, and if I were to take this particular signal, feed it into a spectrum analyzer, so this instrument, what it would do is it would separate out the signal into its different components, just like a prism does. Something similar this one will do. And for example, it will show us, if the spectrum analyzer, it will show us that there are 3 frequency components here. There are 3 sinusoids here, 0.1 kilohertz, 1 kilohertz, and 10 kilohertz. Now, as I said, when we looked at the signal, we could see that there was one high frequency and one low frequency, but perhaps seeing that there are 3 clear frequency components in this particular one was not apparent. But when we do a frequency analysis, then that becomes clear. And it would also tell us what is the magnitude of 0.1 kilohertz, what is the magnitude of 1 kilohertz and 10 kilohertz. So the mathematical tool which we use to analyze it is that when you have a signal, the mathematical tool is Fourier analysis. And when you do a Fourier analysis, it breaks the signal into its different, when the signal is as a function of time, the Fourier analysis will allow us to decompose the signal into different frequency components. All right, so let's proceed with a little bit more discussion regarding the usefulness of a frequency domain analysis. So look at the speech signal. So this is speech signal, let's say captured through a microphone, so it shows amplitude as a function of time. And in this case, the person is pronouncing OH, and this is how the signal in the time domain looks. And in the next case, the person is pronouncing double E, right? So double E here, and that's how the signal looks. And if we compare the two signals, O and E, well, I don't know. I mean, they are different, but what does the difference really consist of? It's not so apparent. There are amplitudes and various kinds of amplitudes, various kinds of variations that we can see here, but it's not easy to characterize the difference between when we say E and when we say O. But if we look at this particular signal and we now analyze it in frequency domain, so we find out what are the frequency components in this particular signal. Well, that's what we call is the spectrum. And so we see that there are 1, 2, 3, 4, 5 peaks are there. If we characterize the signal in terms of peaks, there are 5 frequency peaks at F1, F2, F3, F4, F5. Right? So that's the O signal. And when we see the E signal here, we find the spectrum is different. It's a lot more easier to see the differences between this versus this. The peaks are at different frequencies and the magnitudes may be different. And so you see the spectrum is different from this one. And we can characterize it. Of course, there's still complication. It's not as simple as a sinusoid or 2, 3 sinusoids. It's still complicated, but we could characterize it in terms of, let's say, 5 peaks, and the peaks would maybe are at different frequencies as compared to here. Their amplitudes may be different, and that would help us to understand the differences between the two signals. Now, in this case, of course, O and E, one may not be interested in knowing what is the difference between E and O. But imagine that this were a, let's say, a signal picked up from a ECG, and then its frequency analysis, or some other diagnostic signals, even from not just from a human body, but from, let's say, a machine. So you pick up a diagnostic signal from a machine, and you're trying to isolate what the, let's say, the problem with that particular machine is. So analysis in the frequency domain may help you. This could be the sign of a healthy machine. And then when you see deviations from the sign of a healthy machine, you may be able to characterize the kind of a fault that is there. So the point is, one is not saying that the time domain is doesn't give us insight. What we are saying is that when you take the signal and you split it up into different frequency components, it provides you additional insight. And sometimes, in many situations, even more insight than the time domain signal directly provides. Okay. So as an example, if I again look at another example, if I give you a circuit, it may look familiar to you from our past discussions, but let's not get into that. Suppose some circuit is like this here, and we would like to understand what this particular circuit does. So if I were to look at it, look at its properties in the time domain, for example, one may apply a step voltage here, 0 to 5 volt, and look at what happens. How does the circuit respond to a step? So what happens to the output? Well, if I look at the output, one finds that the output is a decaying or a damped sinusoid. So starts from some amplitude and gradually goes to 0 here. So what we can say is that when you apply a step, the circuit breaks into some kind of oscillation, and the oscillations die down. And now if we ask the question, suppose we change C1, what happens here? So suppose we change C1 to 21 picofarad instead of or 20.93 picofarad. And then we look at the response and we compare the two responses. Well, it's not so apparent what is really going on. we plot the two signals side by side and we see, well, the nature is of course same. Maybe there are some differences, but what exactly is the difference due to change in reduction in the value of C2 is not so apparent here. All right, so maybe one could see there is some phase change, perhaps a little bit of frequency change, something like that one may notice here. But note that if I now look at the analysis of this circuit in frequency domain. So what do we mean by analysis of the circuit in frequency domain? So we'll apply a sinusoid here at the input and we look at the output here, right? So this one is the red one is the input. So we apply 1 volt input. Note that it's a linear circuit, so it doesn't really matter what amplitude you apply here, because the output is going to be proportional to the amplitude of the output is going to be proportional to the amplitude of the input here. Anyway, so we apply 1 volt here and we look at the output here. So this is at a certain frequency. And then what we do is we change the frequency of the input. And we change the frequency of the input, so we sweep the input from, let's say, some low frequency to some high frequency, and we look at what happens to the output sinusoid as a function of frequency, right? So we look at, let's say, 1 kilohertz sinusoid is their input, then we look at, say, 10 kilohertz and lots of 100 kilohertz and 1 megahertz, and of course we see the response is different. The response to 1 kilohertz, note that the amplitude response to 1 kilohertz is different from response to 10 kilohertz, and response to 100 kilohertz is quite different. And response to 1 megahertz is also quite different here, right? So the response is different at different frequencies, but then we are still looking at these responses in time domain. So the idea is that what you do is the amplitude of the input is fixed, but its frequency is changing. So now you plot the amplitude as a function of frequency of the output, right? So if amplitude as a function of frequency. So we look at the output voltage. The input voltage amplitude is fixed, but its frequency is being swept from, let's say, 1 kilohertz to 10 megahertz, right? The frequency is being swept. And the output is also going to be a sinusoid. And we are looking at its amplitude here, amplitude of the output as a function of frequency. So we see something interesting, which was not apparent while looking at the circuit in the time domain. We see that the amplitude of the output is very, very low. It's hardly just because you see the linear scale here is not, doesn't really mean zero. All that it means is that it's very small here, and then the amplitude rises here and then falls again. So what we see here is we can understand the nature of the circuit. The circuit is highly frequency selective, right? So you note that if you think of it as you have a sinusoid as an input, so this sinusoid is trying to go through this particular circuit and emerge at the output. So the circuit, what it is doing is severely attenuating a 1 kilohertz, 10 kilohertz, 100 kilohertz. It's not allowing those signals to pass through, right? In amplitude of V naught is very small. Similarly, high frequency signals are also, if I were to do at 100 megahertz, that also would have come out to be close to zero, small value here. So similarly, high frequency signals are also being filtered out. But there is a signal at around 1 megahertz. The circuit is very sensitive to that particular signal here, right? So the circuit is highly frequency selective. It's not allowing low frequencies to pass through, not allowing high frequencies to pass through, but it's allowing a small band of frequencies here to pass through. So, whenever we have a frequency selective circuit, we often call it, you can call it a filter. And here we can see that it's like a band pass filter. Band pass, there's a small band of frequencies which it allows to pass around that 1 megahertz here. So it's like a highly narrow band filter. If my filter were to allow anything to go from 100K to 10 megahertz, that would be a fairly broad band pass filter, the frequencies that is passing through, but this is a highly narrow band pass filter here. Now this circuit can be very useful because it allows a very narrow band of frequencies to pass through. In one of the homework assignments we had seen that, for example, if you have 2 radio stations or 2 television stations, and one of the let's say radio station is at 1 megahertz, the other one is let's say at this is 200, 400, let's say at 600 megahertz, 600 kilohertz. So you have two radio stations, one at 600 kilohertz, the other one is at 1 megahertz. You want to catch radio station A at 1 megahertz, and you don't want the signal from 600 megahertz to interfere with you. Now all these signals are coming to your antenna. So this VS that you see here could be signal coming from your antenna, and you are interested in only radio station number A with 1 megahertz this. So what do? You pass it through a filter like this. So it will pass that 1 megahertz signal, and that 600 megahertz signal will get severely attenuated. It will not pass through, right? So it's a very useful circuit, which we can see that this particular circuit performs the function of a highly selective, very narrow bandpass filter. The question of what does C1 reduction in C1 do? Well, we can see now. By the way, the amplitude, the voltage that you get here is of course sinusoidal, and we have discussed it has an amplitude which depends on the nature of the circuit, and also has a phase. So we examine the phase. This is how the phase of the circuit looks like. So note that we are looking at the phase of the output, or the angle of the output. We have been seeing in the earlier lectures how to do phasor analysis, and so the output has an amplitude and an angle. The angle is what we are calling as phase. And so we see that phase is, so this is like 90 degrees here. So the phase of the output is 90 degrees ahead of positive 90 degrees positive angle with respect to the input. And then there's a sharp change at around 1 megahertz, which we know is the where my circuit is most sensitive, at sharp change here, and then the phase becomes minus 90 degree. And if you recall from your last lecture, we could see that, with that kind of a discussion, we can tell that the circuit is probably, phase is, positive here. So quite likely circuit is inductive in nature. And then abruptly changing to minus 90, the phase becomes minus 90. So it becomes capacitive in nature. So capacitance tends to dominate at higher frequencies, which we can see from here. It's a parallel combination of L and C. So at low frequencies, the impedance of an inductor is omega L. This is small. And at low frequencies, the impedance of the capacitor 1 over omega C is large. And so they are in parallel, so the inductor dominates. While at high frequencies, when we go here, the inductor omega L the impedance becomes high, but the capacitance 1 over omega L becomes low. So the capacitor dominates here and results in negative phase here. So the phase response is resulting from the nature of inductance and capacitances, their behavior at different frequencies here. Now we said, suppose the capacitor is reduced to 21 PF, what happens here? Okay, so we can see here, the first one is with the original value of the capacitance, and then next case is where the capacitance is reduced to around 20.93 picofarad here. And one can see the effect of change in capacitance is nothing but to change the frequency at which the circuit is most sensitive, from 1 megahertz to a little bit higher than 1 megahertz if you reduce C2. So for example, if you were interested in 600 kilohertz radio station, and you want to catch that instead of this, so we will have to shift this graph towards the left. And this particular then is telling you is that you'll have to increase the value of C2 to shift this center frequency to 600 megahertz, and by that you will be able to catch that particular radio station. All right, so this is not something that we are doing only in electrical engineering. Spectroscopy, looking at a signal at different wavelengths or different frequencies, is very common elsewhere. For example, here you want to understand the nature of a gas, and so you take a laser beam and you look at the absorption of that particular beam at different wavelengths, and you analyze that. And for example, you could see HCl, you could see a spectrum like this. You could see the response at, of course, the frequencies are very high, the wavelengths are in microns, so you could see a response like this here. And this response of the gas at different wavelengths gives us, that these are signatures of the gas that is there, gives us insight into the nature of the bonds and other things. So it's a routine spectroscopy that is used by chemists and physicists to understand the nature of, let's say, a particular element or a particular gas. And so we are doing something similar. We are saying you want to understand the nature of a circuit. Well, let's look at the spectrum of that particular circuit. Let's excite it with sinusoids of different frequencies and look at what happens to the output. Output as a function of frequency, both is magnitude and phase part here. So the idea is analysis of signals in systems in frequency domain often provides very useful insight into the behavior. Okay, so it's a powerful tool that we should incorporate in our toolbox if we want to understand a particular system. So how do we do this? Okay, so let's say we have a linear system, and so linear system is our linear circuit. For us, it's a linear circuit, but it could be other systems also. And we are going to excite it with a sinusoid, and we look at the output sinusoid. And we've been saying that you can analyze sinusoids using the concept of a phasor. So X is a phasor voltage or a current, and Y could be a phasor voltage or current. For example, X could be voltage and Y could be voltage, and the ratio of the two would be the ratio of two voltages, and we may call it as the voltage gain of a system. X could be current and Y could be current, and the ratio of the two we could call as the current gain of the system. X could be current and Y could be voltage. We could call it as the transimpedance of it's a ratio of voltage and current, but voltage is at a different end, current is at a different end. You may call it a transimpedance. X could be voltage and Y could be current. So ratio of current and voltage is conductance, and you may call it transconductance. So X and Y could be anything. But because they are sinusoids, so they are phasors here. Okay, they're phasors, voltage or current and voltage or current here. And because it's a linear system, so note that the absolute value of the magnitude of Y is not of interest. It's the ratio of the Y omega by X omega which is of interest, right? Okay, so that's what we mean by transfer function. We are applying something at the input, and we're getting something at the output. The ratio of output by input is what we call as the transfer function. And we've been saying frequency domain analysis is we need to look at this transfer function as a function of omega, as a function of frequency. Okay, and we are saying that given a system, if you compute this transfer function H as a function of omega, look at in general, because we are talking about phasor quantities, so the transfer function would be complex in nature, and we look at its magnitude and look at its phase. That's going to give us insight into the nature of the system. Okay, so so when we look at a transfer function, and we've been showing you the response to sinusoidal circuit, and we have shown you a plot like this. But note that when you plot things, the way you plot it, the way you represent it is extremely important. So in this case, what we have shown is what we call as a linear plot. It's a linear axis, and this is also linear axis, and we can see the signal here, and we can also see there's perhaps something here. And if it were at even lower frequency, maybe the small blue thing that you see here, perhaps you could have missed it altogether. So often when we look at, because we are trying to understand the system, so we don't want to look at the system over a very narrow frequency range. So in order to understand it, we would like to take a very broad frequency range and to see what are the different frequency components. And so we often, to see a broad frequency spectrum or over a broad frequency range, often the frequency axis is taken in the log scale. So when we take it in the log scale, we can see that there is an additional peak here, and then there is this red signal here. So now it's much more, the plots are much more clear and provide much more insight. Later on, of course, if you want to focus your attention on this, you could plot it in a very narrow range and over a linear plot, and you could do that. But if you want to look at the property of a system, let's say an unknown system, it's best to excite it over a large frequency range and plot the frequency over a log scale here, and that will give you more insight into it. So in general, this is an important statement, that insight. Note that all these analysis that we are doing is for understanding the nature of the system. So insight is a very strong function of information representation. It's an obvious thing, but many times we forget that the same information that you get, you could plot it, you could display it in many different forms, and the way you display it will have an impact on the kind of understanding that you obtain from it. So a simple transformation of axis from linear to a log scale allows us to see the signal, the nature of the system, understand it in a lot better than when we were plotting it in the linear domain here. Okay, so the magnitude of the signal. Okay, so the convention is magnitude. Of course, you can plot it as a number. So the convention in electrical engineering often is to plot the magnitude in decibels, and decibels is the general definition of decibels is starts off with the concept of power. So you have a reference power, let's say P1, and a unknown, let's say power in a signal P2. So you take P2 by P1 and you take 10 log, and you get a quantity which is, you're expressing the power in terms of decibels. Power in electrical signals is often voltage square or a current square. So many times we write it as we will so we may not explicitly talk about power, but we may talk about, let's say, the output voltage, and we may express the output voltage as 20 log 10 V2 by V1 here. So when we convert it into decibels, keeping in mind that decibels power is voltage square, so we'll square here comes out here and becomes 20 log 10 here. And similarly, when we look at the output currents and we would like to express it in dBs, we write it as 20 log 10 I2 by I1 here. And I1 is some reference. For us, V1 may often be 1 volt, let's say, or P1 may be 1 watt, and then the 10 dBs is there. Sometimes the reference may be 1 milliwatt, and so then we will call it dBm. dBm standing for milli. So the reference is 1 milliwatt, and so we will call it dBm. And there are various reasons for using decibels rather than the pressure, or let's say the power directly, and plotting it, power or voltage directly. Plotting it in decibels is useful. One example is, for example, let's say if you're interested in speech signal, for example, a speech signal, is easier to express sensitivity, or it gives us more insight into sensitivity, let's say, of ear to different magnitudes of, let's say, the pressure level that is there. Sound is nothing but pressure waves. So it gives us more insight if we express it in dBs. So for example, 3 dBs is barely noticeable. If you go from 5 dBs to 10 dBs, a 5 dB change, it sounds as twice as loud if you go from 10 to 20 dBs. So note that if you go from 10 to 20 dBs, if we use as a power, let's say 10 to 20 dBs, so what you're doing is you're increasing the signal by a factor of 10. In terms of absolute values, you're increasing the factor by a 10. But the ear is not as sensitive as a factor of 10. Note that it's only 4 times as loud. Anyway, so there are historical reasons and for expressing things in dB. And one of those reasons is, for example, our own perception of hearing. Easier to look at it in the dB scale here. So these are things that, often we will talk in terms of dBs, and so these are the things to remember when you have that ratio that we talked about, the ratio of the two voltages, let's say gain, V2 by V1 gain, let's say here, if it's 1000, then it's 60 dBs, if it's 100, it's 40 dBs, 10 is 20 dBs, 2 is 6. Then 1 is of course 0 dB, 1 over square root 2 you'll see has a special meaning here. 1 over square root 2 is minus 3 dB here. Okay, 1 over square root 2, 0.5 is minus 6 dB, and so on and so forth here. Okay, So decibel scale often reveals more information about behavior, just like a log scale here. So decibel scale is also, note that you are taking log and plotting it. So it's also a log scale here. So for example, so we saw that instead of plotting it on a linear frequency scale, if you plot it over a log frequency scale, we are able to see the signals much more clearly. Similarly, if I were to take this scale here and convert into decibels, I will get more insight here. So the whole thing is converted into decibels, and now we can see a lot more of the variations with more clarity than in the previous case. Note that in here, of course, all this part was appearing to be 0, and all this part was appearing to be 0. We can see it's not really 0. So it has it's continuously reducing, of course, and it's continuously reducing, and we can see what is the strength of a signal here compared to the peak value is easier. For example, at this particular point, the strength of the signal is 75 dBs smaller compared to maybe 70, if we take it close to 0. So it's like maybe not 75, maybe let's say 70 dBs below this particular one. And so signal is 70 dBs below here, and somewhere else you may say the signal is 50 dBs below here. And once you understand what the dB scale really means, then you can easily correlate. 60 dBs is like 1,000 times larger. Minus 40 is like 100 times smaller, right? So we will often be plotting representing our magnitude of the signal in decibels. Along the y-axis, and we'll be plotting the frequency over a log scale, right? So over a log scale, because we want to see how the system responds over a very wide scale of frequencies there, right? So this plot of decibels, so converting the amplitude or converting the magnitude of the transfer function into decibels and plotting it on frequency on a log scale is a standard plot that we use to understand the system. And in honor of the person who made a lot of contributions to frequency analysis of circuits, we call it a Bode plot. Okay, so for example, if the signal is 1 volt here, it's of course 0 dB, and if we go here, we find is 20 dBs below, minus 20 dBs here. So if we go back, minus 20 dB means 0.1, right? So the signal is 0.1 volt here. When we go here, well, it's 40 dBs below this, right? So 40 dBs below here, so it's going to be 0.01, and so on and so forth. Here, 60 dBs below is going to be 0.001, 1 millivolt here. Okay. All right, so a few more things, simple things, but to keep in mind. When we're talking about let's say a range of frequency from 10 to the power 3 to 10 to the power 4, a factor of 4, we call it 1 decade. So for example, if somebody gives you a range of frequencies and says the signal is varying in this manner over 2 decades, right? So instead of saying it's varying like this from 10 to the power 2 to 10 to the power 4, sometimes we say, well, the behavior of the signal is like this over 2 decades, right? So this is 1 decade here, 10 to the power 2 to 10 to the power 3, 10 to the power 3 to 10 to the power 4 is another decade here, okay? So we're saying 1 decade and another decade, 2 decades. Similarly, so number of decades is log f2 by f1, okay? Now, obviously, please don't get confused between 100 and 10,000. If I divide it by 10, it's not really two decades if you were talking in terms of years of time and things like that. Different meaning here. So 1 decade increase in frequency, and then another decade frequency increase. So total increase in frequency is 2 decades here. Sometimes you will hear the word octave. So it's a factor of 2. So when you 50 to 100 you go, you say a factor of 2 increase. So you say this frequency is 1 octave higher, and you could say 1 octave lower. And then when you're talking about octave, you take the ratio of the 2 frequencies. If you want to find out how many octaves are there between F2 and F1, take the ratio and take log 2, because we are talking about a factor of 2 here. If you're talking about how many decades are there between 2 frequency ranges, take the ratio and take a log with respect to 10. Anyway, so how do we determine the transfer function? So we said transfer function is will provide us insight into the nature of the system. So let's say we have a circuit like this RC and we want to find out its transfer function. Output, how the output responds to the input. So it's all about sinusoidal analysis. So input is VST is Vs0 cos omega t. And the transfer function is nothing but the phasor output voltage V0 divided by the phasor input voltage Vs as a function of omega, right? So in phasor analysis, now we leave the time domain part here. We only represent it by Vs angle 0 here. And in phasor analysis, we said convert everything into their complex impedance value. So resistor stays a resistor. Capacitor becomes 1 over j omega c. Now analyze this. So it's a simple analysis, V0 by Vs. You can easily analyze this and show that the transfer function is 1 by 1 plus j omega cr. Okay, so it's just a simple voltage divider. So you can get 1 plus j omega cr here. So now we said, okay, so you obtain a transfer function. So obtaining transfer function is straightforward. We have done phasor analysis, convert the circuit into a phasor circuit, and calculate the ratios of the output and input, whatever output you're interested in versus the input that is given here. So you calculate the transfer function. The next thing is you take the magnitude of it here. So magnitude is a complex number. So magnitude would be 1 over square root 1 plus omega square c square r square. And you take the phase part of it, the angle part of it, because j is here. So it's minus tan inverse omega cr. So what we are saying is the transfer function is a representation of the nature of this particular circuit that is there. And now to understand the transfer function, we are going to plot the magnitude as a function of omega, and we're going to look at the phase as a function of omega. All right. So let's look at the amplitude part here. So amplitude, remember we said we will not plot amplitude as it is, but we'll convert the amplitude into decibels, right? So since we are taking the ratios of two voltages, so the decibels would be 20 log 10 h omega, and the square root and all that comes out here. So it's minus 10 log 10 1 plus omega square c square r square, right? So this is the circuit. Let's put some number here, 1 k and 1 microfarad. And so this is the plot here, the plot of the magnitude of the transfer function expressed in decibels as a function of frequency, plotted on a log scale, a large range of frequency. Note that we are going almost from 1 hertz to 1 megahertz, a range of frequency which is how many decades? 6. Okay, 6 decades here, from 1 hertz to 10 to the power 6, so 6 decades of frequency we are plotting. And we are plotting this as a in decibels. And so what we see here is 0 decibels. 0 decibels meaning, please note that h omega is nothing but a log of v0 by v1. So 0 means v0 by v1 is actually 1. And so when you take log of 1, you get 0 here. So 0 decibels actually means, when you see 0 decibel, it actually means the signal is simply able to pass through. v0 by vs is basically equal to 1. So 0 decibel is an indication of signal simply going through the system. That is there here. So we can see that all these lower frequencies are able to pass through. And then we come to a break, a transformation of here, somewhere here around this particular point. And now the higher frequencies are getting attenuated, right? They're getting attenuated. And so let's explore this in a little bit more detail. So the transfer function is 1 plus omega square c square r square. And the CR, we can express it as 1 plus omega square by omega 3 dB. You'll see why we are calling it. So omega is nothing but frequency. So we are calling it a 3 dB frequency, the CR here. All right, so omega 3 dB, we are writing as 1 over RC. And this is in, of course, radians per second. And you convert it to hertz. Frequency in hertz will be 1 over 2 pi RC. And so note, why are we calling it 3 dB? Well, if I put omega equal to omega 3 dB here, so it becomes log of 2, and log of 2 is 0.3, and so it becomes minus 3 dB. It becomes minus 3 dB. All right, so that's where the name of 3 dB is there. So what is the significance? We said, well, the signals of lower frequency are 0 dB. 0 dB means the system is like transparent. The signal just goes through. And at around here at this value here, at this particular part here, note at this particular frequency here, the signal has fallen by 3 dBs, right? The signal has fallen by 3 dBs here. So it's like, 3 dB is a transition point. It's a point where the signal is beginning to now, in this case, the signal is beginning to get attenuated here. So beyond this frequency, the signal is getting attenuated here, and so that's the 3 dB point here. Okay, so this is an important frequency which characterizes the system, because below 3 dB frequency here, the signal is practically, you can see here, is like 0 dB. After the 3 dB point here, the signal rapidly gets attenuated here. Okay, so it's a transition point. And so that's so when we are characterizing a system, of course the detailed plot is there, but in the detailed plot we've identified a frequency called 3 dB frequency here. So that's an important parameter of the system. What is the 3 dB of the system? Well, that is, in this case, omega 3 dB is 1 over CR, or F3 dB is 1 over 2 pi CR here. The other thing is what happens, we've seen that the signal starts to get rapidly attenuated for omega much greater than 3 dB here. So if we take this transfer function, and for omega much larger than omega 3 dB, we can neglect the factor 1 here, and then it becomes simply omega square by omega 3 dB square, and we can take the 2 out, and it becomes minus 20 log 10 omega by omega 3 dB. So what this says is the following, that in the regime where you are a frequency range where you are much larger than 3 dB frequency, a 1 decade change in frequency. So if you increase omega by a factor of 10, then my transfer function would decrease by 20 dBs, because 1 decade, a factor of 10, and so this will be 20 dBs here. So we characterize a system that there is a slope here. The slope here, the rate at which the signal is getting attenuated is, we call it 20 dBs per decade for 1 decade increase in frequency. So if I'm here, and then, or let's say at 10K, if I'm here at 10K, and then if I go to 100K, you can verify from the plot here, if you go from 10 to 100K, the signal change, the change in the signal is a factor of 20. So that's the characteristics of the system. It attenuates once you go to a frequency, let's say significantly higher than the 3 dB frequency, then the signal is attenuating at a rate of 20 dBs per decade. That's the nature of the system. So we have qualitatively we can see that it's like a low pass filter kind of a thing. It passes the lower frequencies and it's attenuating higher frequencies. So that's a qualitative nature of the circuit, that is acting as a low pass filter. The second thing is the 3 dB frequency, the frequency at which, so if we were to, the red curve is the exact curve, but if we were to approximate it, we could approximate it by a straight line here, and then at the 3 dB point we can draw another straight line with the slope of 20 dB per decade here. So it's an approximate representation of this. Okay, and so 3 dB point tells us the transition point, the frequency beyond which the signal starts to get severely attenuated. At 3 dB point, the signal is 3 dBs smaller. Okay, 3 dB smaller here. In terms of amplitude, the signal is 1 over square root 2. In terms of power, the signal is half at 3 dB point. Okay, the signal is, in terms of power, the signal is half, and in terms of voltage amplitude or a current amplitude, the amplitude at that particular point has become 1 over square root 2 as compared to its amplitude at lower frequencies, right? So if the signal is 1 volt here, at the 3 dB point, the signal's amplitude would be 0.7 volt here. And the power at that particular point would be half, okay? So that's the nature of the system here, okay? So we can, through this analysis in the frequency domain, we have identified several things, that the nature of the filter is a low pass filter, that there's a transition frequency called F3 dB frequency here. Beyond F3 dB frequency, the rate at which the signal is getting attenuated because is 20 dBs per decade here. Okay. All right, so as we said, this is also called the 3 dB frequency is called a corner frequency. Corner, because of the simplified plot that we have drawn here, there's a change here, there's a transition here, there's a corner here. Okay, so 3 dB frequencies are also called corner frequencies, also called half power frequencies. Okay, so let's take this is example. H omega is, let's say, 10, 1 plus j. If we plug in numbers, and let's say we get 1 plus j omega 10 power minus 3 here. So if we were to understand what is the nature of the system here, let's say you've done the analysis and you've obtained the transfer function. So what you do is you take the converted the amplitude of it in decibels. So you take 20 log 10 h omega here. So that comes out to be 20 minus 10 log 10 1 plus omega squared by omega 3 dB squared here. And omega 3 dB you identified as 10 to the power 3 here. So rewrite this as omega by omega 3 dB. So it's 10 to the power 3 here. And you can convert it into frequency by dividing it by 2 pi. Now for frequencies, we can see now this is the function that we need to plot and analyze. So we can see that for omega much less than omega 3 dB, for omega much less than omega 3 dB, this log is, this thing is practically 1. And so it's basically equal to 20 dBs. This part then becomes 0, it becomes 20 dBs. And then the other one, which is easier to plot, is for omega much larger than omega 3 dB. So in that case, for omega much larger than omega 3 dB, 1 we can neglect here, and so the function becomes 20 minus 20 log 10 omega by omega 3 dB. So we can plot it like this here. If we were to plot as a function omega, at low frequencies we can draw a line is 20. It's like 20 at low frequencies. And then this part here, 20 log 10 omega by 3 dB here, at higher frequencies we can see that is falling at a rate of, if I make omega which is 10 times higher than omega 3 dB, or if I take two frequencies, omega 2 and omega 1, and the ratio is a factor of 10, then in terms of dB, the change will be 20 dBs here, right? And so a simplified plot, which you will see more in the next lecture, is that there is a omega 3 dB is 10 to the power 3 here, so we identified that point. And we're saying, note that at that point, beyond that particular point, my signal is going to change as 20 dBs per decade. Below this particular point, the signal is like constant at 20 dBs. That is there here. And you combine the two together, this plot and this plot here, it becomes like this here. So it's a simplified plot of this particular transfer function here. By looking at values considerably lower than 3 dB and then considerably higher than 3 dB here. So the plot is fine here, the plot is fine here. At this particular point, we have just connected it in a very simple manner here. It's a little bit more complicated here, right? There's a curve here. And but the simplified plot gives us a lot of insight. That it tells us that the breakpoint is 10 to the power 3, and that the signal is attenuating at 20 dBs per decade. Below that, the signal is, the circuit is transparent. Okay. All right, so, so let's see the usefulness of the plot that we just obtained. The circuit, for example, the circuit that we just made here, and how we can use that particular circuit. So let's say my signal. So in this case, what I did was I generated a composite signal, which is made up of 0.1 kilohertz and 10 kilohertz. And let's say my interest is, so the signal that is there, artificially generated signal made up of 0.1 and 10 kilohertz. Let's say the signal is actually coming from some source. And your interest is in basically 0.1 kilohertz, and 10 kilohertz is like a noise for you. And you want to remove the 10 kilohertz signal, okay? So we see that circuit like this is useful for us. Circuit like this is useful for us if we take the transfer function that we just have, 1 over j omega, 1 plus j omega by 10 to the power 3 here, this transfer function that we just talked about, and we pass a signal through this. We pass a signal through this transfer function, which is represented by here, by this circuit here. So if you pass it, what will happen is 0.1 kilohertz signal is 100 hertz signal is considerably smaller, a factor of 10 smaller than 1 decade lower than the 3 dB part here, omega 10 to the power 3 here. and therefore more than a factor of 10 lower than this. So what we can do, it means that the signal will pass through, right? So if the amplitude of, let's say, both the signals is the same, 0.1 kilohertz signal will pass through. On the other hand, if it's 1 volt, it will go to the output is 1 volt here. Okay, so for example, we've written 0 dBs here, so it will pass as 1 volt here. On the other hand, 10 kilohertz signal. So 10 kilohertz signal would be somewhere here, 10 kilohertz, and 10 kilohertz is about 1 decade higher than the break frequency or corner frequency or 3 dB frequency of 10 to the power 3. And the slope of the line is 20 dB per decade. So it means that approximately, because we know that the graph is not exactly piecewise linear like this here, but we can say that the 10 kilohertz signal would be 20 dBs lower. Will get attenuated by 20 dBs. Okay, and therefore we can see 20 dBs, remember, is a factor of 10. Okay, so the signal, initially both were 1 volt. So the output would be, the lower frequency signal will come out as it is, 1 volt, but the higher frequency 10 kilohertz signal will get attenuated by a factor of 10. 20 dB per decade, 20 dBs means attenuation by a factor of 10. 40 dBs means 100. Minus 40 dB is 100, minus 60 is 1000, and minus 80 is 10,000. Okay, so 20 dBs, because 10 kilohertz is 1 decade higher than this, and is decreasing at a rate of minus 20 dB per decade. So this sinusoid will become 20 dBs lower. 20 dBs lower means a factor of 10 lower here. Okay, so that's how my output is going to be, and this is how it looks like. Right, so here you could see both the low frequency and the high frequency all clearly, and here you could see the low frequency component is pretty much the same. The high frequency component has become attenuated. Now suppose you're not happy with it, you want the higher frequency signal to get further attenuated. So what do? Right, so your signal is still made up of 0.1 kilohertz and 10 kilohertz. You would like 0.1 kilohertz to pass through, but you don't want 10 kilohertz to pass through. You want to attenuate it even further, because you can still see the signal is not that clean. So now what you could do is, if you stay with the system like this, you'll try and play around with 10 to the power 3. You will say, well, if I want to attenuate my 10 kilohertz signal even more, maybe I should shift the 3 dB frequency 10 to the power 3 to a little lower. Right, lower here maybe, but you can't, because the signal that you want to pass through is 0.1 kilohertz or 100 hertz, so you can't shift it too much. You can't shift this signal to for example, I can't shift the signal from 10 to the power 3 to, let's say, 100 hertz, because then if it's 100 hertz 3 dB frequency, then my 100 hertz signal will also undergo an attenuation of about 3 dB. So it will also get attenuated, which is something that maybe I don't want it. So you can play around a little bit with this number here. You could shift it here and thereby increase the attenuation of 10 kilohertz even further. But if you're looking for substantial attenuation of 10 kilohertz, then maybe what we are looking for is, we would like to preserve the 3 dB frequency at, let's say, 10 to the power 3. But the rate at which it's decreasing, can we make it 40 dB per decade? Can we increase it to 40 dB per decade? Then what would have happened is, if you could do this as minus 40 dB per decade, then, so if you could do it at 40 dB per decade, then this 10 kilohertz signal would become a factor of 100 lower here, right? So that way then, the signal would become cleaner here. So this is what we did here. We took the circuit RC and we added another RC block here. So one RC acts as a filter, then we filter it again. And when we do that, note that this is with one RC circuit here, and these are with two RC circuits. Note that the signal becomes much cleaner here. Okay, and this is the difference between the two circuits. In one case, the signal is falling at 40, the transfer function is falling at 40 dB per decade. And the other one, the transfer function is falling at 20 dB per decade here. Why is it falling like this and all that, we'll see later on. But what we are trying to do is illustrate to you the usefulness of frequency analysis, the plotting of transfer function in dBs and looking at it over a wide frequency scale and analyzing it in terms of the attenuation rate in terms of dBs per decade and 3 dB frequency. These are very useful concepts in designing and of these systems here. Note that this is one stage of RC filter, this is two stage here, this is three stage here. So we can control the rate at which the signal gets attenuated.